In this third and final video for section 4.9, we'll do a few more examples. We've got some more trig functions to take a look at, taking the antiderivative of, as well as an e function, a natural log function. So here we go. So we left off with example number 5. So here's my 6th example. And here we're taking the antiderivative of the secant of 2x times the tangent of 2x with respect to x. All right, so once again, we have to first of all think about which function is going to give us a derivative that has secant times tan, and then how do we deal with the multiple of 2 here. So remember that the derivative of the secant function is, let me try that again, secant of x times the tan of x. Okay, so the derivative of secant is secant times tan. So we're almost there. We know that our answer is going to have a secant in it, but we also need to deal with that 2x. So remember in that last case, what we did was we took the chain rule piece, the inner argument, and we kept it inside, but then we had to divide by that constant in order to adjust. So we have to add c, and now I'm wondering if I remembered to add c at the end of my last video. If I didn't, catch me on those things, because you're going to forget sometimes too, and you don't want to as much as possible, because you'll lose points if you forget to add a constant c. So let's try not to do that, although we are human, of course. So I want to just give this a quick check. So let me take the derivative of 1/2 times the secant of 2x plus c. Notice that I can divide the whole thing by 2, or I can multiply it by 1/2. It means the same thing. All right, so in order to do that, I can always take my 1/2 and I can factor it out. And I can separate this into 2 terms and take the derivative of each term. So the derivative of secant of 2x is secant 2x tan 2x, use the chain rule and multiply by the derivative of the inside, which is 2. Don't forget that you have that 1/2. And then over here, the derivative of any constant is always 0. So let's clean it up and see if it did work out for us. So I'm a little bit ahead of you guys here in processing all of this, but 1/2 times 2 cancels each other out, which remember was the whole point of dividing by 2, is so that we could undo that 2 that we would get from using the chain rule. So that leaves us with the secant of 2x times the tangent of 2x, and because we added 0, that's it. So to complete the check, we just want to go back to see if that is in fact what we were trying to find the antiderivative of, and it did work. So that is the answer. All right, let's take a look at one last example that has this same type of thinking. And this one is the antiderivative of the cosine of x over 2 with respect to x. So notice in this one, I again have a constant multiple, but that constant multiple is a fraction. So think about the antiderivative of the cosine function. The antiderivative of cosine would be sine. And the reason is that the derivative of sine is cosine. So if we reverse it, that's what we get. We have that inner argument, which means that if we were to take the derivative of this function, we'd end up multiplying by 1/2 to finish off the chain rule, which means we need to divide this by 1/2. Remember that dividing by 1/2 is the exact same thing as multiplying by 2. So hopefully I can go through this one a little bit more quickly because you're starting to catch on. but that should be the result. 2 sine of x over 2 plus c. All right, the very last example for this section is to find the antiderivative of e to the negative 10x with respect to x. So let me do a little side note over here. We haven't looked at this yet. But what is the antiderivative of just plain e to the x with no negative 10 constant multiple? And this is the best function ever because the derivative of e to the x is itself, e to the x. So that means that when we reverse the process, the antiderivative of e to the x is also just itself. So this is a really cool function where the derivative and antiderivative are the same. So now we just have to figure out what do we do with that negative 10x. So it's very similar to those trig functions. We can't use power rule here. I should probably stress that. So this is not a power function. Remember, power functions are in the form of x to the p, and we have e to the, I don't know, ax, let's say, e to the ax. So these are not the same. The exponent is the base, and then we have a constant power. Down here we have a constant base and an exponent that is the variable. I don't know if I said that right over here. Variable base, constant exponent. Constant exponent, I can't get that straight. Hopefully you guys see what I'm trying to point out here. This is a constant base and a variable exponent. Anyway, you can't use the power rule. So think about taking the antiderivative of e to the regular x, and you'd get e to the x. So when you take the antiderivative of e to the negative 10x, think about how you're going to adjust for that constant. Well, if you were to take the derivative, you'd have to then multiply this by negative 10 because of the chain rule. So to undo it, you'll divide by negative 10. So hopefully that is what you would have guessed, but we get e to the negative 10x over negative 10, and it just seems more proper to write that negative sign on the top, and then the 1/10 or the divide by 10 plus c. And that's what we should get for an answer there. Again, negative 1/10 is the same. Okay, so those are all your antiderivative problems. You really have to try to use that reverse thinking, and instead of relying on a formula all the time. If you know your derivatives really well, then I think you're going to have a pretty easy time. The last objective in this section 4.9 is to be able to solve initial value problems. So essentially, initial value problems, what they do is they have you finding an antiderivative, and then they give you some additional information so that you can solve for c. Remember, when you're taking the antiderivative of a function, your answer can be an infinite number of different functions by adding different number constants or different valued constants. So here we're finding a particular solution or a specific solution by finding the exact constant in the antiderivative. So let's say that we have, for example, a derivative that's given to us as x squared minus 2x. And we're given that one additional piece of information. We're given that there is a point on f. Okay, so the original function f has a point or an ordered pair where if x equals 1, then y equals 1/3. And so what we're asked to do is to solve the initial value problem. That would be the directions. And so what that really means is to find f with the specific value c. So what we're going to do is we're going to set up an antiderivative. We know what the derivative is. We want the antiderivative of that function. So that would be the first step, is to find the antiderivative. And remember that you can set this up using the constant multiple rule and the sum rule, and find the antiderivative of each piece. So here I would get x cubed over 3 minus 2 times x squared over 2 plus some constant c. And all of this is telling us what our f function is. Again, we knew what f prime was. We use the antiderivative to get back to f. Simplify that just a bit by canceling out those 2's. And we have a generic function f that represents our antiderivative. We want a specific function f where we know that if x equals 1, y equals 1/3. So what we're going to do is we're going to take this and we're going to plug that in. X equals 1 and y equals 1/3, so that we can solve for c. So 1/3 equals 1 cubed over 3 minus 1 squared plus c. This is kind of nice here. 1 cubed is 1, so that gives us 1/3, which means that if I subtract that from both sides, they cancel each other out. Here, I've got -1 plus c, which tells me that c equals 1. That's helpful, but it's not the final answer. The final answer was to find the function f. And now we have an exact answer where we've solved for the constant c with antiderivatives.